Hi, I'm Shania Nicole Muñoz Cardoso, and today I'm going to talk about my Marriott Bottle Report Experiment 1. In this experiment, we built a Marriott bottle to study its discharge into operating regime, constant emptying flow and non-constant flow. For this, the height of the water with respect to the emptying time, as well as the air inlet and water outlet velocities were analyzed. The results obtained were that the speed is constant as long as there is an air inlet that allows the pressure to be the same as the atmospheric pressure. While if there is no such air inlet, this speed varies. In this, we obtain a constant velocity of 1.0 plus minus 0.5 meters per second. The results obtained were conclusive, as the theoretical value lies within the uncertainty of the measurement. Marriott's bottle consists of a glass jar bottle with a lateral hole near the base in which a horizontal straight tube can eventually be inserted, and a tube that fits perfectly to the throat of the bottle, staying in a vertical position. The tube at the bottom is used as a drain tube, while the tube at the top allows the pressure inside the bottle to be the same as the atmospheric pressure. Therefore, this device will provide a constant pressure that will deliver a constant rate of flow. The Marriott bottle is one of the applications of Bernoulli's principle, specifically Torricelli's theorem. The development of this experiment is significant if it allows us to study the combination of mechanics and hydrodynamics that is applied in our surroundings, for example, in the operation of microfluidic injection devices. Moreover, this experiment is valuable in our learning process as engineers because it will allow us to perform an experiment in which the results might be heavily influenced by the uncertainties present. This report pretends to show a detailed examination of the construction process and operation of Marriott's bottle, involving the acquired knowledge about uncertainties. To have a better understanding of the concepts involved in the functioning of Marriott's bottle, we built our theoretical framework in which we explained and presented Bernoulli's equation and Torricelli's principle. The materials used to carry out the experiment were a cylindrical plastic container, an atmospheric pressure tube, the drain tube, a seal, measuring tape, a channel container to receive the water from the cylindrical container, a stopwatch to measure time, and 3 liters of water. We also presented the experimental setup and a schematic of the bottle in which we can observe distances H, D, and D that will be measured in the experiment. Here we can see tables 1 and 2, presenting the measurements of the bottle and the measurements of water level height over time. For the experimental analysis, we calculated the areas and their uncertainties, which can be seen in table 3. And lastly, in table 4, we reported the calculation of average velocities corresponding to each value of time and average water level. To calculate the uncertainties, the process was as follows. To calculate values for H, we obtained the average H for the 5 measurements done of the experiment for each time value. Then to calculate the uncertainty for H, we obtained the sample standard deviation of the average value obtained for H. To calculate the velocity in, we obtained delta H by subtracting the initial H value and the last measurement of H, and dividing it by the current value of time. To calculate the uncertainty for V in, we did the square root of the sum of the squares of the uncertainty obtained for H and the uncertainty given for time. To calculate velocity out, we use the continuity equation solving for V2, obtaining the presented equation. To calculate the uncertainty for V out, we obtain the sum of the percentile uncertainties for area 1, area 2, and velocity in to get the percentile error for the out. Then we converted set percentile value to an absolute error. Finally, we rounded up the values obtained using the uncertainty. To achieve a better analysis of the results obtained, the following graphs were elaborated. Figure 1 presents the dependence of water level H in the bottle on time t, while figure 6 presents the dependence of the average velocity of the water at the outlet in the bottle on time t. As can be seen in figure 5, the height decreases linearly until approximately 90 seconds, where a slight curve is observed in the values of H. On the other hand, in figure 6, it can be seen that the speed is constant after 5 seconds with a value of 1.0 meters per second. And in the same way, approximately at 90 seconds, the speed ceases to be constant and begins to decrease. Considering that we were using a Marriott bottle, the rate of change of height was expected to be linear and the exit velocity to remain constant as long as the inlet tube was below the water level. The foregoing is due to the fact that at 90 seconds, the water level was lower than the level at which the atmospheric pressure vertical tube was located. So there was no constant air inlet that would allow a constant diffusion rate. While the water level remains above the upper end of the mentioned tube, the bottle has bubbles inside, which allows checking that there is a constant air intake. Based on the theoretical framework, at this point, the diffusion rate can be calculated with equation H. Comparing our results with what was consulted in the theoretical framework, it can be determined that the functioning of the constructed bottle was correct. When calculating the output velocity theoretically using Torricelli's theorem, we obtained that the velocity is 1.25 meters per second. The value obtained theoretically is within the reported range of uncertainties, since the probable range calculated for the experiment result is from 0.5 to 1.5. Therefore, the result obtained agrees with the expected result. However, it is important to measure that the uncertainty value obtained is high, of 50%, and therefore the measurement process was not very precise. Despite the fact that the results obtained were quite good, a lot can be improved about the experimentation. The results may have been altered by not filling the bottle perfectly or by moving the bottle when refilling between each measurement. For this experiment, it was found that in Marriott's bottle, while the water above the lower end of the atmospheric pressure, the decrease in H will be linear and the diffusion velocity will be constant, obtaining in our experiment a constant velocity of 1.0 plus minus 0.5 meters per second, which agrees with the expected result. At 90 seconds, both the decrease of height and the speed are no longer constant if the water level is lower than that of the vertical tube. This experiment is important when we analyze the operation of Marriott's bottle, reporting all the results with their uncertainties, which can strongly affect the results in an investigation. The computation and interpretation of uncertainties was significant during this experiment to elaborate and improve the analysis. In this work, the uncertainty obtained for the outlet velocity allowed us to observe that the theoretical outlet velocity lies within the uncertainty of the experimental outlet velocity. In further analysis, it remains to determine how the exit speed is affected depending on the height at which the lower end of the vertical tube is placed. Thank you.